Then we come to dominant pole compensation. Okay, and we usually use for dominant pole, we use integral or type 1. When I say integral, means make HLC nothing but integrator, not HLC, sorry, the H comp. So, H comp S equal to K over S. And push omega naught outside omega UGB. So, how far we need to push it? How do we decide? I mean, you can make omega UGB just slightly less than omega naught, but what would happen? Is that possible? Like we can do that and make it stable? So, Q factor will come into picture, huh? So, let us see what would happen. So, this is your integrator. After putting that integrator, this is what it is doing. So, I am plotting the LGS magnitude. Let us say I make omega UGB equal to omega naught. That is what I try to do, but I am not considering Q naught factor. So, what would happen? In this case, it will peak here, it will do like this. So, if Q factor was not there, the gain should have crossed 0 dB here, but due to Q, your gain is at UGB does not remain 0 dB, but more than 0 dB, and you know the phase there is almost touching 180 degree, minus 180 degree. So, you do not have any phase margin as such. Okay. So, gain at omega UGB is greater than 0 dB and phase margin is close to 0. So, this makes it unstable. So, how do we fix this? Which means omega UGB should be even less. Now, let us make omega UGB equal to omega naught over Q, Q naught. So, how will it look like? LGS, what will be the gain here at UGB? 0 dB, okay. So, it will do like this and okay. And this is your okay. So, this is stable or unstable?
Depends on the amount of shoot.
Shoot. I mean, you cannot consider it stable, huh? You are, I mean, what is the condition for stability? Your gain 0 dB and phase shift 180 degree. 180 degree in the negative feedback or total 360. So, the phase is crossing here 180 and gain is touching 0 dB. So, it is again unstable. Unstable because again so if you look at a UGB, you may get a good phase margin at UGB, but the problem is the phase margin at omega naught is reduced, or you can say in other word the gain margin is basically 0 here. Okay. Because gain equal to 0 dB at omega naught. Okay. So, gain margin equal to 0 dB, which means your omega UGB we choose should be less than how much? Omega naught over Q naught, and for minus 20 dB gain margin, omega UGB should be equal to omega naught over 10 times Q. Okay. So, if I know omega naught is known, Q naught is known, all I need to do. So, what do you, so you have an integrator in the loop, what do you need to find? So, let us first or take this guy maybe. Beta K over S, GPWM is and HDRV is VDD over VM, H of LCS. So, what is your gain from here? So, if I call beta VDD over VM equal to, let us say I call it KU0. Okay. So, your LG becomes KU0 K over S, let us call it KI. KI means gain of your integrator. Okay. So, how do you choose the gain? So, this factor KU0 into KI should be how much? So, if let us say this was only Ki over S, so what will be your UGB in that case? Ki, huh? And if you have a RC integrator, it will be 1 over RC. If a GM, it will be GM by C. So, and you know the UGB. So, now this factor has become KU0 into KI and UGB is already known. So, this will become omega UGB, which is nothing but omega naught over 10 times of Q naught. So, your Ki should be over Ku 0 10 times of Q naught. Omega naught is known, Q naught is known, okay, or omega naught over Q naught is this term, R loss over L plus 1 over R load into C. So, you can from here you can calculate your, so 1 over Ku 0 or 10 times Ku 0 and this will be your R loss over L plus 1 over R load C. Okay. And you can make that assumption here also. For no load condition you can put R load equal to infinity. So, that will become R loss or L simply. So, you can calculate, or if you have already calculated here omega naught and Q naught separately, you can substitute that as well. So, let us say you have already calculated from this formula, where is that? Yeah, Q naught max from here and omega naught you already know 1 over square root LC. So, you can substitute directly there also. Okay. And Ku 0 is known from your VDD is known, your VM is known. Okay. So, if you want 20 dB gain margin, then we have to follow this particular expression where your integral gain should be 1 over 10 times Ku 0 and in the bracket you have R loss over L plus 1 over R load C, and if you are looking at, as we already saw, that your Q will be maximum at no load. So, this term may go away and leftover will be, so for no load so your Ki will be simply 1 over okay. So, let's take an example. By the way, why are we doing all this? I mean, why do we need to model basically each and every module? So, small signal is valid for continuous time signal, and this is a sampled system. If you look at switching system, okay, just like you do your switch capacitor circuits, okay, you have to model your switch capacitor resistor and replace it with the continuous time, and that is how you follow. You first design the continuous time and then convert to a sample time. So, you do all the analysis in continuous time for a small signal, and then when you do loop gain analysis, it is valid for a small signal continuous time system. So, you have to convert each and every basically stages in a continuous time, replace, model it, and based on your specification you have to design, and then after that you convert everything into sample system. So, PWM has to be replaced with the gain module, whatever the gain of that modulator is, your compensator with the transfer function, everything, and after that once you analyzed everything, you found the parameter, what basically compensation parameters you require, or here it is all you need to find the value of Ki based on your specifications given. So, once you find that, you can replace each and every block with its equivalent circuit, and you can run your transient simulation with PWM clock. Okay, so but if you directly go to a sample system, then it will be very hard to analyze this in terms of stability. So you always design in continuous time and then convert into a sample system or switching system. So example is, let's say your L equal to or VDD equal to 1.8 volt, Vref is 0.6 volt, then you have L or better FSW, so let us consider RDS on equal to 50 milliohm and DCR, RDCR also 50 milliohm. Okay, and Vm equal to 1 volt, your ramp amplitude. So Ku0 you can calculate. What was Ku0? Beta? VDD by Vm into beta. How much is this? 1.8 divided by 1 into beta. Beta is how much? 0.6 volt Vref, output is 1.2 volt. So beta should be 1 by 2. Okay. Vref by V out. What is R loss? What is R loss? RDS on plus RDCR. 100 milliohm. L is already given, 3.3 microhenry. Find your Ki. How much is Ki? 1 over 10 times, yeah, correct. How much is Ki? 1 over 10 into 0.9, R loss is 0.1, 3.3 microhenry, 3.367, 3.367 kilo radian per second. Okay, so now we need to design the integrator for this with Ki equal to this much. So let us say I am using GM by C integrator or GMC integrator. So GM by C equal to or Ci equal to Ki, correct? This is 3.367 kilo radian per second. So let's say I choose GM 10 micro ampere per volt. So your CI will be how much? So smaller GM you choose, the capacitor value will be small. Yes.
In the K expression, we didn't take resonant frequency.
Which K expression?
Ki omega naught
Into
below.
No, this is correct. Huh? Omega naught over Q naught is replaced by this. So it's incorporated there. In this transfer function, what is the in the denominator? What was the coefficient of S? Omega naught over Q naught, and what was that? That was this, huh? So I just replaced the whole thing omega naught by Q naught with this. So whether you replace individually omega naught and Q naught, ultimately you are going to get the same thing. So CI will be GM by KI. How much?
0.029 nanofarad.
0.029.
029.
I don't think it's correct. Okay, let's do it. 10 micro. 10 micro is how much? 10 power minus 5 over KI 3.367. 10 to the power 3. Okay. So 1 over 3.367 multiplied by 10 power minus 8. How much is this?
It's around 0.029 into 10 power minus 1. 0.29 into 10 power minus 1.
No, 10 divided by 3.67. Huh? 10 divided by 3.367, 2.97 nanofarad. Huh? Okay, correct. So how will your circuit look like? So this is your R loss, which is 100 milli. This is 3.3 microhenry. Ten microfarad. So beta, let's say, okay, so beta is this is Vref. GM this is 0 to 1 volt. Okay, and this is your VDD, which is this is V control. So now, so the same thing I have put in this simulator. Okay, so I have replaced this with the 1.8 volt. I was looking at a continuous time. So this what we have drawn here is the switching circuit. Okay, so you have to replace this modulator with the gain. So, gain will be VDD over, sorry, the total gain including your driver will be VDD over VM. So, 1.8 divided by 1, that is simply 1.8, that is what I have done here, 1.8, okay. And this is your one gain of your PWM modulator, okay, 2.97 nanofarad, and GM is 10 micro, 10K, 10K. So, I have broken the loop here. So, 3.3 and 100 milli inductor and RDCR, sorry, R loss. So, we designed it for gain margin of 20 dB and which will be around resonance, okay. Probe. So, 0 dB is crossing here because we have killed the bandwidth by making the integrator gain very low, but we have to see where the phase is crossing, or your phase margin is basically around 0, 0 in the sense like it is going to 180 degree. Probe phase. So, this is your resonance, okay, and this is your phase. So, due to negative feedback, if you look here actually, this is your resonance, okay. This integrator will cause 90 degree, okay. The reason you are seeing it starting 180 because I have a resistor here. So, your DC basically phase shift will not be minus 90, which is for the integrator. The reason I have put because it is a floating node, so simulator will not converge. So, you have to put high value resistor here. It is a 10 mega. If I increase this giga ohm, maybe this curve will shift here. So, you have a pole here basically due to this RC, and in reality you will get a, I mean you cannot get an ideal integrator. Huh? So, at DC it will always start with 180 degree, and then from here to here you can see a, so from 90 degree plus 92 it is going towards minus 90, okay. You can see here y axis it is showing here minus 83, okay, because it's your RLC is lossy here because of your R loss, otherwise it would have crossed to, so if R loss is 0 it will cross to perfect 90 degree, sorry 180 degrees, or okay, your total phase shift at resonance. So, which means you are only 7 degrees away from your 0, a total phase shift of 0 or 360 degrees, okay. And we have to make sure that here gain is much less than 0 dB, so that we do not get any oscillations or instability. So, let's move in the different axes. Okay. So, you can see here so 0 dB is here, it is minus 20, and that is what we designed for, minus 20.